students, let us start with Henry-Borel theorem for R. Henry-Borel theorem for R. Let J is equal to closed interval AB be a closed and bounded interval in R. Be a closed and bounded interval in R. Then for every open cover of closed interval AB admits a finite subcover, that is, closed interval AB is compact. What is the Henry-Borel theorem for R? Let J is equals to closed interval AB be a closed and bounded interval in R. Then for every open cover of closed interval AB admits a finite subcover, that is, this closed interval AB is compact. Okay. Let us see next theorem. Any compact subset of a metric space is closed and bounded. What does the theorem say? Any compact subset of a metric space is closed and bounded. Okay? Let us see proof. Let XD be any metric space. Let XD be any metric space. Okay? Let K is a subset of X be compact. Okay? We have to show that this K is closed and bounded. Okay? Consider this X. This X metric space, and this is a K is a subset of X. Okay? 6. Any x0 belongs to capital X. Okay? Consider the open cover B of x0, n such that n belongs to set of natural numbers. This admits a finite subcover for K. 6. Any x0 belongs to capital X. Consider the open cover B of x0, n such that n belongs to set of natural numbers. This admits a finite subcover for K. Say B of x0, n, j such that 1 is less than or equal to j is less than or equal to n. Okay. It follows that or implies what k is a subset of b of x0 comma n, or here say capital N, for n is equals to set nj such that 1 is less than or equal to j is less than or equal to small n. Okay. Here we get k is a subset of b of x0 comma n, where n is equals to nj such that 1 is less than or equal to j is less than or equal to capital N. Or here we can say that k is a subset of union I runs from 1 to n b of x0 comma nj, because our k is a compact set. So k is a subset of this open sphere, therefore k is compact. Therefore k is compact. Sorry, not compact, it is bounded. Okay. Here we have shown that this k is bounded. Now it remains to show that k is closed. Okay. Now our claim is k is closed. Okay. Let x does not belong to k. Okay. Here our assumption is x does not belong to k. For any, sorry, not any, for each y is belongs to k using Hausdorff property. Using Hausdorff property. Hausdorff property of x, we can find ry such that b of x comma ry intersection b of y comma ry is equals to 5. X does not belongs to k. Suppose here is x. Okay. For each y belongs to capital K using Hausdorff property. First of all, see what is Hausdorff property. For any x comma y belongs to capital X with x is not equals to y, means x and y are distinct points in x, there exists open set U such that x is belongs to U and open set V such that y belongs to V such that U intersection V is equals to 5. For any x comma y, suppose this is your metric space x, and x and y are two distinct points. There exists a open set U which containing x and open set V which is containing y, such that intersection of this U and V is empty. Okay, this is the Hausdorff property. So here for each y belongs to k. For each y means, suppose here is y1 point, here is y2, y3 and so on. we can find Ry. Ry is nothing but Ry1, Ry2, Ry3, Ry4 and so on. B of x comma Ry intersection B of y comma y is equal to 5. Suppose here is this is R1, this is R2, this is R3 and so on. Okay, this is by using Hausdorff property. Obviously, see here students, B of x comma Ry means nothing but it is the open sphere centered at x with radius Ry or R1, sorry, Ry or Ry1. This is equal, or you can say that Ri. So, see here students, B of x comma Ri intersection B of, here is B of y comma Ry is equals to 5. Okay. The collection B of y comma Ry such that y is belongs to K is obviously an open cover for K. Why? Because B of y comma Ry is say open sphere, and you know that every open sphere is a open set. So in this collection, every open sphere is open set. That's why this family is a open cover for K. Okay. Since K is compact, we have a finite subcover. Say B of yi comma Ri. 1 is less than or equal to I is less than or equal to Ri is nothing but Ry. Okay, where Ri is equal to Ry. Okay, clearly if you say B is equal to intersection R B of x comma Ri, okay, is open set. Obviously, intersection I B of x comma Ri. This is the intersection B of x comma Ri is an open set. Okay, which is containing x. Okay, and why this intersection B of x comma Ri is open set? We have seen one result, it is a theorem in first chapter, that is finite intersection of open set is open. Therefore, intersection I B of x comma Ri is open. Okay. Now we claim that B intersection K is equal to 5. Now this is our B, and our claim is this B intersection K is equal to 5. Let it possible X is belongs to B intersection K. Okay. Since K is a subset of union I runs from 1 to n B of y I comma r I. Since K is a subset of this, because this is a open cover for K and K is compact, so this open cover has a finite subcover. There exists some J such that X belongs to B of Yj comma Rj. There, see here students, K is a subset of union of P of Ri comma Y, B of Yi comma Ri. So there exists some J such that X belongs to B of Yj comma Rj. Okay. Since P is a subset of B of X comma R J for all J. Okay. Why this is? Because B is the intersection I B of X comma Ri. This is the B. So obviously B is a subset of B of X comma R J for all J. That implies, see here students, here X belongs to this open sphere and X obviously it belongs to this open sphere, so X belongs to B of Yj comma Rj intersection B of Yj comma Rj. X belongs to both open spheres B of Yj comma Rj and B of Yj comma Rj. Not here Yj, here is X. Okay, but this is a contradiction. Why? Because see here students, B of X comma Ry or Rj intersection B of Y comma Ry is equals to 5, and here we get X belongs to this intersection, so this is not possible. Hence, which is a contradiction. Hence, hence our assumption, which is a contradiction. Hence our assumption X does not belong to K. Sorry, which is a contradiction. Okay. Therefore, for all X does not belong to K, we can find an open set U such that U is a subset of X by K or K complement. You see here, for X does not belong to K, we can find an open set U which is a subset of K complement. That implies X minus K is open by definition of open set. So therefore K complement is open, so K is closed set. Hence our proof of theorem is completed.